Hello students, today we will see one more example for canonical transformation. We'll see how do we solve harmonic oscillator using canonical transformations. Okay, now for that we'll consider a one-dimensional harmonic oscillator. So you know the Hamiltonian for such a harmonic oscillator, which is given by kinetic energy plus potential energy. So in that case, you can write kinetic energy as P square by 2m, which is easier to remember because you know what is kinetic energy is usually written as half mv square, and instead of this I can multiply it with m as well as divide it with n. So now you can see what is mv. Mv is momentum p. So it is p square divided by 2m. So that is what we have written here as kinetic energy. And the other is half k x square is usually what is written for potential energy of a spring or a harmonic oscillator. So instead of x we have denoted as q for coordinate. Okay. So what you do is that we just rearrange this equation. We are taking out 2 is common in both the terms and m is also taken outside. So finally what you have is p square plus m is taken outside, so m is multiplied here, m into k q square. And you know from the relation omega angular frequency is given by k by m for a spring. Okay, so in that case we can replace m into k, m into, or instead of k I can write from here as k is equal to m into omega square. Okay, so substituting that, already you have a m over here and you'll get one more m from k, so it become m square omega square in k and q square. Okay, so here what is special about this equation is that both the terms are appearing as squares. So we prefer to have a Hamiltonian which doesn't have any explicit dependence on any one of the coordinate. That means we should prefer to have cyclic coordinate. Since it is appearing as squares, how can we omit the squares, one coordinate from square terms? Yeah, we can make use of trigonometric relation. So we will consider a canonical transformation of the form. Let p is given by any function of p, capital P into cos q. Similarly, small q coordinate is given by f of p by mq into sin q. So one contains cos term, then other contains sin term. So substituting that, you will get cos square q plus sin square q, which can be taken as 1 as per the trigonometric relation. Okay, so for the time being we will consider such a transformation equation to be applied into this Hamiltonian. So substituting that, you'll get the new Hamiltonian, which is same as we have studied it as h plus dou f df by dt. But you know it is a conservative system, so it is dependent, it is not varying with time. Here also you can see it is not varying with time, so we can consider k as same as old Hamiltonian. So the new Hamiltonian is same as old Hamiltonian. Okay, because it is a conservative system, Hamiltonian will not change. So now you can replace p square as f of p cos q as p whole square plus m square omega square. Instead of q I can write it as f of p by m omega sin q whole square. Okay, now you can say f of p is common in both the terms. We are taking that outside. 2m is already there outside. Remaining is cos square q from first term, and from second term m square omega square will cancel off and remaining is sin square q. So here you can see it is just a trigonometric relation, cos square q plus sin square q is 1. So we are end up with a relation which depends only on capital P. Capital Q has been omitted out. So the Hamiltonian, whether it being alter or the new Hamiltonian, can be expressed in the form of or as a function of one of the coordinate alone. Okay, so what does that imply? Yeah, that capital Q coordinate is not present in Hamiltonian, which means capital Q has become cyclic. How do you made it cyclic? Yeah, by substituting the appropriate canonical equations. Okay, so that is the whole purpose of doing canonical transformation, to get a cyclic coordinate in the representation. So now let us, we need to find more what is f of p and all, and what is a generating function and all. So let us see that. So for that we need to omit, or we need to get it into a proper form to decide what kind of generating equation we can use of. So here I am just taking the ratio of P and Q. So here you can say f of P will cancel off, remaining is only m omega will come up, and cos by sin is cot Q. And you can say P is equal to Qm omega cot Q. So here you can see you have a relation which is the function of small q and capital Q. So which kind of generating function can give a relation which depends only on small q and capital Q? Yeah, it is given by f1. f1 is the function which gives a transformation which depends upon small q and capital Q. So once we are inferred from the relation what the generating function is, we can make use of the transformation equation of f1. What are the transformation equations of f1? f1 is a function of small q and capital Q. So what should I have been finding out? Small q undengile we can find out small p by varying f1 with respect to already non-variable, that is q. Similarly, capital Q is already there, so varying it with respect to capital Q, you will get capital P, which is the conjugate of Q. Okay, and a negative sign is also there for the new system. Okay, so we'll make use of these two transformation equation and we'll arrive at what is F1 and what is the equation is actually. So now you already have in the previous slide we have obtained P is equal to Q m omega cot Q. So now you can substitute, instead of P I can write it as dou F1 by dou Q is equal to Q m omega cot Q, or I can integrate out F1. So what is F1? Integrating m Q omega cot capital Q with respect to small q. That was a differential. So all other being constant, Q is integrated out, so it becomes m omega Q square by 2 cot Q, which is the generating function. Now we can make use of the generating function over here. We can substitute for F1. So the cot Q has to be differentiated. In this, everything else is constant. Cot Q has to be differentiated with respect to Q. So what is cot Q? It is minus cosec square Q. So negative sign will goes off and you will get small q. By rearranging this equation you get it as 2 will come up here, so it becomes 2p divided by m omega, and that would be in square root because we are taking the root here to get q. So this becomes 1 by sin cosec q, which is sin q. Okay, just by rearranging we'll get it as small q as square root of 2 from here, 2p, and m omega will go in the denominator into cos square q, square root cos q arm, that will also come in the denominator. So 1 by cos q is sin q. So that's how we obtain this relation for q. Now we need to find out what is capital Q. So if you compare equation 2 and equation 4, what is equation 2? Equation 2 is actually we have chosen the canonical transformation of this form. Small q is equal to f of p by m omega sine q, and what we have obtained from the relation is small q is equal to square root of 2p m omega into sine q. So by comparing these two, it is easily can say that what is f of p, what is f of p, we just have to equate the coefficient of sine q. So equating that, you will get it as f of p by m omega is equal to square root of 2m by m omega. So 1 root m omega will cancel off. So finally what you have f of p as square root of 2p m omega. Okay. So now you have Hamiltonian, which is given by h, which is given by f square p by 2m. We have seen it. So substituting for f of p, we have 2p m omega whole square. So square root become nil. So divided by 2m. So finally what you have is omega into p. So the new Hamiltonian is a function of capital P. Again you can see capital Q is not explicitly present. That means capital Q is again cyclic. Now let us consider the conjugate. So if Q is cyclic, corresponding momentum must be a constant. That we have already seen. So which is given by, from this relation capital P is equal to, just rearranging you will get it as h by omega. So now you can write down what is the equation of motion. Only if you write down the equation of motion and solve it, then only the solution will be complete. Okay. So first what we do is, Hamiltonian was written and it was reduced to this form, and then you find out what is f of p and substituted it back, and then you have what is, you can write down the equation of motion. So one of them is q dot is equal to dou h by dou p, Hamilton's equation of motion. Another form is, so just differentiating h with respect to p. H is differentiated with respect to p, you will get it as omega. So solution will be q dot is equal to omega, or q is given by integrating it out with respect to time. So it become omega into time plus constant of integration. And for coordinate, the constant is denoted using alpha. Okay. So now instead of capital Q in the equation for small q, I can write it as small q is equal to square root of 2p by m omega into sine of omega t plus alpha, which is one of our solution. So solution of a problem means we must know what is q and coordinate and momentum. So the coordinate is already been got. Now we need to find out momentum. So how do you get momentum? You have those equations f of p and p, or h is equal to omega p, and q is already found out as omega t plus alpha. So now the solutions are, q is already found out. So instead of capital P, I can also write it as e by omega from this relation. So it becomes 2e by m omega square. So that way also you can write it down, which is the usual expression for harmonic oscillator. And small p is given by the canonical transformation equation f of p into cos q. And what is f of p? Square root of 2p m omega. So substituting that and substituting for capital Q, that is omega t plus alpha. So you will get the relation as p is equal to, again p into omega is Hamiltonian, which is energy, total energy, capital E. So you will have the equation as square root of 2me cos of omega t plus alpha. So these two are the solutions of harmonic oscillator. Okay, so thank you. That ends our chapter on canonical transformation.